Hello, welcome again to GG413 Geological Data Analysis. This is video 4 of the series of videos on the Introduction to Statistics. And the topic of this video is on section 1.5.5, and I'm going to retitle it. It's really the relationship between a sample mean and variance and the population mean and variance. And a very important concept theorem in statistics is the central limit theorem. And I'm going to read a definition of the central limit theorem taken from Davis's textbook. And that is, if a number of samples, say M samples, are taken from any population, it doesn't matter what the distribution of that population is, but if it's taken from any population, and the mean is computed for each sample, the sample means will have a distribution that tend towards a normal distribution, a normal frequency distribution, or a Gaussian frequency distribution. And the tendency towards normality increases with the size of each sample. So let's say we have a population that we're sampling from, and we take there are n data points in each sample, and we take a mean of our first sample, and so we might represent the mean and standard deviation as with a line like this. So this is our first sample mean and standard deviation. The mean of our second sample might be slightly different. The mean of our third sample is slightly different yet, and so forth. So the horizontal axis is the value of x bar that we're measuring. And if we were to show the frequency distribution of those means, so again, the vertical axis is frequency, and this is x bar, we might get something that looks something, I'm not sure what it looks like, but say it looks like something like that. And what the central limit theorem is saying is that if we take the distribution of the means for our M samples, it will tend towards a normal distribution. Our normal distribution is a bell-shaped distribution. It's symmetric on either side of the mean. It's our Gaussian function. We'll get into that a little bit more in detail. But what you need to know is that the distribution of those sample means will be distributed like this normal distribution, or in other words, the central limit theorem is stating that the sample means is an unbiased estimate of the population mean. So the sample mean, so the mean of x bar as written here, so the mean of x bar, not x tilde, tend towards mu, the population mean, as n tends towards infinity. So again, this is the sample size, and mu, of course, is the population mean. Okay, so an important aspect of the central limit theorem is the mean of all of our M sample means tends towards the population mean. A slightly different outcome is the grand mean also tends towards mu. Okay, so I hope I've illustrated that concept to you. The other aspect I'd like to emphasize is that this is true for any population. The population itself doesn't have to be normal. It can have any form. And you'll still get a normal distribution of the sample means. So this is a figure from, this is all from Davis, and I'll put a PDF of this online for you to get and include in your notes. And what this shows is this is the population. And as you can see, the distribution, the frequency distribution of the population is not Gaussian. It's most frequent on the edges of this diagram, unlike a Gaussian population. But and here's an example of 5 samples of 5 points each. So M, for some reason my pen wants to draw down there. So here we have M equals 5 samples and N equals 5 data points in each. And so for the first sample, we get a data point here, 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 and here. And X bar is somewhere around here. And so forth for the second sample and the third. And as you can see, for each sample, the data values tend to be near the ends on this plot, consistent with the frequency of those values occurring in the population. But as you see, all the values of the means tend to cluster near the middle, and they tend to cluster in a normal distribution, even for this somewhat strange population distribution. Here's another example, and the top plots here, these are population distributions. And these are, so this is, so the horizontal value here is X in the population. And the plots below show the distributions of X bar for different size samples. So here's N equals 2, N equals 4, and N equals N, not M. N equals 25. And again, each of these axes represents the distribution of X bar. So if we take a whole bunch of samples with 2 data points each, the distribution of the means starts to become a bit more symmetric and more like a Gaussian distribution than the actual population distributions. As N increases, the tendency towards the bell-shaped curve increases, as explained by the central limit theorem. So we've discussed that the mean of the sample means is about equal to the population mean. So that tells us that if we have numerous samples, we can take either the grand mean or the mean of the sample means, and we get an estimate for the mean of the population. Now, it's also true that the sample variances have a mean value approaching the population variance, so sigma squared. So that is to say that the mean of S squared tends towards sigma squared as N goes to infinity. So this is one way of estimating the variance or standard deviation of the population. Yet another property is that the standard deviation of X bar going back to the sample mean, and we'll write that as Sx bar is related to the population standard deviation by Sx bar is equal to the population standard deviation divided by the square root of the sample size. And this is true for an infinite population. And if the population is finite, the standard deviation of the sample mean is equal to the population standard deviation divided by the square root of n times the square root of the population size minus n divided by the population size big N minus 1. Okay, so this is for finite population of size n. So this is a second way of relating the properties of the population, the statistics of the population, to the variance of the statistics derived from the samples to the parameters of the population. And then the last relationship is that the variance of the variance of S squared is related to sigma squared by the variance of S squared is equal to 2 over the sample size minus 1 times sigma to the 4th power. Or if we write that in terms of standard deviation, the standard deviation of the variance is equal to the square root of all this and times sigma squared. And I'd like to point out this is equation 1.103 of Wessel. I've just written it in a slightly different form to be consistent with using S for the statistics measured of the sample.